This video will discuss ideal gases, the ideal gas law, and some general properties of gases. So when we're in a gas form, there is a tremendous distance between the atoms in a gas, so much so that it doesn't make a great deal of difference whether we have one type of molecule or another type of molecule, different elements. The atoms or the molecules are extremely far apart, so we can write a general equation that analyzes or allows us to discuss changes for all types of gases, regardless of what actual element or molecule is making up the gas. So we get this ideal gas law. Ideal gas law. In one form, pressure times volume equals the number of moles of gas times the gas constant times the temperature measured in kelvins. So PV equals nRT. The pressure needs to be the absolute pressure, not the gauge pressure. It needs to be the true pressure, not the gauge pressure. And pascals would be our standard unit. That's not a strict requirement for solving problems. There are ways of solving problems so you don't have to use pascals. Volume, cubic meters. And again, certain situations, liters or cubic centimeters would be allowed when you're taking ratios of two ideal gas law equations. And for my students, I'll be showing you how to do that in a separate video and in class. So pressure times volume. V is not velocity, V is volume in this context. N is the number of moles of gas that are present. To calculate this, you need to use the number of individual molecules that are present and divide by Avogadro's number. The gas constant is roughly 8.3 when you're in units of moles and joules for the energy, and T in Kelvin. So PV equals nRT. Or pressure times volume equals the number of individual molecules times Boltzmann's constant times temperature in Kelvin. So depending on which information you're given, if you're given the number of moles, then you'd use PV equals small nRT. If you're given the number of particles, then you might want to use PV equals capital NkT. And again, the R is a gas constant, K is Boltzmann's constant, and T needs to be in Kelvin. Do not use temperature in Fahrenheit or temperature in Celsius. And one common problem-solving technique is having two conditions. Put subscripts, P1 V1 equals N1 RT1, and then divide by P2 V2 and N2 RT2. And in so doing, the constants will cancel out, and some of these quantities will be the same. Maybe the pressure is held constant, maybe the volume is held constant, maybe the number of particles is held constant. So it just simplifies the calculation. If you're just doing one calculation, if there's just one unknown, then and you're given values for all the other unknowns, then you do want to use P in pascals, V in cubic meters, N in moles, with standard gas constant of around 8.3, and temperature in Kelvin. But if you're doing the ratio type analysis for problems, P1 V1 divided by P2 V2, you can have the pressure in atmospheres or the pressure in pascals. You could have the volume in meters or the volume in cubic centimeters. And then N1 RT1 divided by N2 RT2, the temperature there still must be in Kelvin. Don't use Celsius. And that's what I'll say about that, and we'll go on to other concepts here. What's a mole? Well, the OpenStax College textbook has a nice graphic here about a mole. You might have a rough idea of how big one table tennis ball is. If you had a mole of them spread around the Earth, the sphere of the Earth, so that's going to be about 40 kilometers deep of just tennis balls. And here's, for example, Mount Everest. So a mole, 6.02 times 10 to the 23rd objects make a mole. A mole is a large number. Avogadro's number is a large number. And why do we have pressure? Well, as molecules encounter a wall, they bounce off, and the molecule applies a force to the wall applies a force to the molecule, pushing it back here. That's the basic reason that we have force. At the bounce, the wall is applying force to the molecule. By Newton's third law, the molecule is applying force to the wall. The force is the net force for the collection of gas impinging on the wall creates a force that's perpendicular to the wall. And again, pressure equals force over area. Molecules moving at a lot of different speeds and a lot of collisions occurring. So we get a sort of a statistical effect here with the ideal gas law and with pressure equals force over area. We don't try to calculate the force just from one molecule bouncing off of a wall. Instead, we use the measurement of the pressure of the gas times the area gives us the force. Later chapter, we'll talk about sound waves. Sound is propagated through a gas, a liquid, or a solid, but going through a gas, the speed of the gas molecules plays a role in the calculation of the speed of sound. Molecules do not have one set speed in a collection of molecules. We have what's called the Maxwell-Boltzmann distribution of speeds, and you notice that some speeds are very high, some speeds are slow, and there is a most probable speed, there is a root mean square speed that is characteristically used to describe a gas. It's just a nice statistical measurement of that takes into account the non-symmetric curve that we have here. But the distributions of speeds, the probability that a certain molecule will have a certain speed or in a range of speeds would be described by this curve. And we do have the situation that there are some molecules traveling much faster. You can see 1200 here versus 400 at this peak. Traveling 3 times or 4 times or 5 or 6 or 7 or up to 10 times the most probable speed. The distribution of speeds depends on the temperature. And if the temperature is higher, then we're going to get more velocity, higher velocities for the peak and higher velocities for say 2% of the fastest particles. They'll be traveling at a faster speed than 2% of the particles at this lower temperature. As the temperature goes up, the speed goes up, and we'll do some calculations with that. Why does the moon not have an atmosphere? Earth has an atmosphere. We're about the same distance from the sun. Well, the moon does not have enough gravity to retain an atmosphere. The temperature at our position in the solar system is such that the molecules and atoms move fast enough to escape the moon's gravity. The Earth does have enough gravity to retain an atmosphere. And then on the ideal gases again, the ideal gas, the molecules need to be very far apart from each other, and they need to only exert force at the time of collision. So if we get down to this condensation point in temperature, the gas is no longer ideal. Here, the neighboring molecules are experiencing significant force even when they're not in contact. So ideal gases are gases that are not near to condensing. Ideal gas has to have a higher temperature than the temperature at which the gas would condense. So those are comments on the ideal gas law, ideal gases. Look for some example videos and examples in class in solving problems using the ideal gas law.